stream starting here, and you're gonna need this. Hey, this this your channel, and this one. Yes, sir. This is the OBS lights. Okay, that's the OBS. And what about here, right? And you need to stop this one. Don't understand. That's next. Okay, no problem. Still here. Open widget. This. We go to that soon again. And tomato cloud, even cloud outside here. First time. Yeah, first time. And to YouTube. This one too, right? Where is that? Here. Zoom to YouTube. Up here. And we go to zoom again, and we're gonna need to change this one. Oh, error. What happened? TBI. We have to connect to the Wi-Fi here. Yeah, it's already connected. Yep. Yeah, Zoom is working, I think. Yes. Zoom is working, and we stick ourselves to this one. Otherwise, you're gonna need to restart your machine like this, and press that. Oh, yeah. ชวินมาแล้ว and 42แล้วนะครับ the next person, we need the next person right here in yes, check it right there. It's YouTube. Oh, please, YouTube. Yes. Okay. Finish, and build share on it. Build share. What time starting? Right, it's gone. And this one, right? Yeah. You need to go live like this. Use another account. Log in YouTube. Yes, this one. And once you connect YouTube, create event 16, yes, and no, this one go live. 3 people already turned on that. And right here, you have to check in this here, please. Yes. Public yes. There are 3 channels. You can check it here. 3 channels. Exit 3 channels. And yes, please go there. All right. My error. Master title is invalid. Okay. Okay. This is Zoom, I think. Yes. It's Zoom, right? Not made for kick. Oh no, why not? This is Zoom channel, right? Zoom channel. Yes. And for the people who want to go to get into theเครื่องนะครับแป๊บนึงนะครับต้องรีสตาร์ทใหม่กัน I trick lesson ตั้งชื่อยาวซิมแลปจบyes, let's get into this is the Zoom version. I have to go to this one. Where is that? Okay, this one. โอเคชัยสิทธิ์พิมพ์ชื่อมาแล้วนะครับเดี๋ยวนะครับเครื่องนี้มันมีปัญหานิดนึงครับคือชื่อตั้งชื่อยาวแล้วมันไม่ไปครับหยุดก่อนดีกว่านี่หยุดโอเคสตรีมครับไปตั้งชื่อยาวของ live go live next YouTube create event in here F3 no stream up only yes go live I hope it works now. Yeah, okay, it works great. All right. So good morning everybody. Good afternoon everybody. We are late in 7 minutes. Team is inactive. What's the problem? Okay, yes, we will continue our story here. Once you finish it last time the detail of standard model of elementary particles, right, which serve as many basic things in physics, right? Even the elements in space, it is based on several particles here. What you have seen in this table, the elementary particle, and let's check the internet connection to this device. Yeah, it's already correct. All right. Okay. Yeah. The next thing is that there is another physics theory that could explain something about the behavior of the wave particle of the any object, right? And that idea came from a French physicist in 1924, Louis de Broglie. Okay, I don't know how to pronounce it exactly, but Louis de Broglie, maybe you can pronounce like that. He presented a new idea in his PhD thesis. Okay, only at the doctoral degree level. Okay, in PhD thesis only. Okay, with the same kind of these, you can also do that. Okay, if you are eager, you want to pursue a PhD or the doctoral degree at a university. Okay, you don't need to be in a high level like in the in a professor level or something like that. Yeah. Louis de Broglie has presented an idea which is quite different from many works in at that time. Okay, in yeah, because he wanted to he wanted to explain the wave behavior of several particles, especially the tiny particle like something on the atomic scale. Okay, something with radius of angstrom, right? It is 10 less to negative 10 meter. Okay, a free electron with mass m moving with speed v. Okay, if you have a very tiny particle, this his theorem is very good to explain something which is very tiny like electron, right? Electron is moving with speed v. Okay, let's say this is the mass of electron, which is 9.1 10 to negative 31 kilogram, right? Yeah. He said that this is a particle, a very tiny particle. It's a kind of lepton, actually. Yeah, electron belongs to the class of leptons, right? As you know from the elementary particles in that standard table. Yes, the electron here is moving with speed v, and de Broglie said that these particles also generate a wave, okay, electromagnetic wave with the wavelength lambda, and he proposed that of course from the classical physics, the momentum of this particle could be found by the conventional expression, right, which is p. Okay, p stands for momentum, and m, right, on the right hand side, p equal to m times v. M is the mass of the electron, and v is the speed of the electron particle. So that's the classical way of the momentum, right? You heard that before in Mathew 4 or Mathew 5, right? And yeah, it's exactly the same way as the photon, which is described by lambda is equal to h by p. And once you substitute p by mv, you're gonna get lambda of electron that also generate the wave. Where is the color chain? Okay, here. This electron would generate also the wave. Okay, and the wavelength here of this one could be found from this expression. Lambda is given by h by mv. You know h, right? H is the Planck constant that you have seen before, right? We have seen before, which is on the scale of -34 or something like that, right? That's the Max Planck constant. Yeah, before that, in the topic of photon and so on. Why do we have this? Why? Oh my god. ทำไมหน้าไหนครับ Oh. Where is the Planck constant? Oh. ไกลมาก Here. Okay. The Planck constant is 6.6260715 times 10 to -34 joule second, right? And that's the typical scale, typical unit. And if you want to express it in the appropriate scale, like in electron scale or atomic scale, it's going to be reduced by divided by 1.6 10 to -19, right? And the quantity of Planck constant will remain like 4.1 10 to -15 electron volt second, right? Yeah. And yes, here you can just simply use the Max Planck constant to this one, okay? And the mass is the mass of any particle, and at the first stage, Louis de Broglie has observed this behavior to electron, right? And but this expression is valid to any particle, whether it's big or not, okay? And yeah, yes, you can use this expression to anything, okay? Even bigger, it's also available, okay? It's also valid, like the object in a bigger scale, like tennis ball, right? Tennis ball, which is big, much bigger than the electron, okay? It's also possible to apply this formula, but the important thing is that once you know that H is on the scale of -34, right? 10 to -34, and if you have more mass, right, the wavelength, okay, mass appear as the denominator, the wavelength will be very, very tiny. And once you have very tiny wavelength, it is very hard for human at the moment to have any measurement device to observe this, okay? And that's the limit right now. But if you have small, very, very small amount of mass, like the tiny particle, for example, electron or any particle in this table, so in that case, yeah, it may not hard for human to detect the wavelength of this duality, which is called wave particle duality, okay? The two phenomena that appears from the particle movement, right? And that's called duality of wave and particle, okay? And that's called wave particle duality, okay? Which has the expression like this: H equal to M divided by MV. Okay. Furthermore, de Broglie has observed that this relation is valid through many kind of particle, not only electron, right? It's valid also to protons, to any particles that you may have seen in the standard elementary table, okay? So yeah, that's the generality of the expression by Louis de Broglie. Yeah, Now let's get into the first example so that you can see the idea how we could apply the Louis de Broglie. Oh, that's very far. Okay, the Louis de Broglie expression lambda. Oh, it's too far. Yes. This is a kind of modern physics, right? We are talking about the idea of wave particle duality, and the next thing is gonna be the Werner-Heisenberg principle of uncertainty. Okay, where yeah, we will talk about that later. I will not waste our time to do that. Okay, this example asks us to find the speed and the kinetic energy of a neutron. Okay, that has the de Broglie wavelength as 0.2 nanometer. Okay, it's in the opposite way, right? Yeah, usually we need to know first the mass and the velocity or the speed of that object first, and then we're gonna get the output or the outcome as the wavelength, right? This wavelength is called de Broglie's wavelength. Okay, yeah, but in this example it asks us something in the opposite way. Okay, in the reverse way. Okay, yeah, and let's talk about that. Yeah, the speed and the kinetic energy, right? So we draw here a paper in yes, it's something about neutron, right? And neutron is gonna be what is the notation of the neutron? I forget that. Okay, neutron is 0 and 1 here. Okay, there is only positive charge. Single single element here at the superscript, and there is no charge at all, right? There is no charge, and one element here. Yeah, neutron has the mass of 1.67 times 10 to negative 27 kilogram, right? That's the mass of the neutron, and yeah, that's the basic quantity we need to keep in mind. And what they say is that okay, they want to know the speed of neutron. What is that? And furthermore, they want to know the kinetic energy of the neutron. And what is that, right? Given the de Broglie wavelength of the neutron has 0.2, or in the SI scale, you're gonna have 10 to negative 9 meter, like that. Okay, you convert it to the SI scale already. All right, yes. Let's get back to the de Broglie wavelength expression. Lambda equal h by mv, right? This one, equation 57. Lambda equal to h by mv, right? But in another term, you're gonna see that if you convert it to, because we need to deliver the first answer, right? We will be h by m and lambda, right? Yeah, you would get this expression, and you could find the speed or the velocity for the neutron particle like this, right? You just substitute the mass of the m here as the mass of the neutron. You could get Vn, right? For the second quantity, Kn, okay, you know that Kn is the kinetic energy of the neutron. Okay, this particle is moving with speed Vn, the velocity or speed of neutron, and m is mass of neutron, v speed of neutron. But once you take a look at the first equality in equation 57, you know that lambda is h by p, right? And you could solve this equation for p, which is the ratio between h and lambda, right? And we're gonna find the relation between the kinetic energy and the momentum, right? Yeah, as we know, P from equation 56, P is equal to M and V, right? But what we have here is only MV, right? MV square. So if you write down further, it's gonna be 1 by 2 MN VN. Oh, sorry for that. I'm stupid. Okay, MNVN square. But if you write it like this, it means that you have M square, right? Which is not correct. We have only a single M without any square, right? So we're gonna divide this one by Mn. Okay, and yes, of course, it's gonna remain 1 by 2 and p momentum of the neutron by mass of the neutron. Okay, if you take a look at this, okay, so we could get the you can calculate it in many ways anyway. Okay, you can also calculate first the velocity, and after that you substitute velocity to the expression, and then you yes, kinetic energy, and then you substitute the mass of the neutron is also possible, or you wanna calculate first the momentum and then you substitute the momentum to the expression. It's up to you. Okay, I just show you several ways to reach the destination of the answers. Okay, so let's get into the first quantity, the speed of the neutron, right? So you know that h is 6 blah blah blah. Yes, h is 6.626 times 10 to negative 34, and you divide this one by the mass of neutron, and you just take a look at that one, right? It's 1.675 times 10 to negative 27, and that's in the kilogram scale, right? H and M and lambda. Lambda is the wavelength, which is stated here is 0.2 nanometer, but you have to use the typical scale, the SI scale, which is 0.2 times 10 to negative 9, right? Meter, and you put it into the calculator, you're gonna get somehow like 1977 times 9, and the unit for it is meter per second. Okay, and that's the speed of the neutron, this particle. Okay, I know you know that the Bruyn wavelength is valid for several particles, right? Several types of particle. And yes, the next thing is that we need to calculate the kinetic energy for the neutron, right? Kn is 1 by 2. Mass of the neutron is over there, right? Which is 1.675 times 10 to negative 27. And v square, v is the speed what you have got. You have just recently got 0.9 m square, right? And you leave it into the calculator. I don't understand, right? You leave it into the calculator, you're gonna get somehow like 3.2 7 joule, right? The unit of the energy or the work is joule, right? Yeah, you get something like this, but no, but there is also 10 to negative 21, which is very tiny, right? The energy on the order of 10 to negative 21 is very small, so it's not appropriate. Okay, if you work in a bigger scale, like the engine of the car or the power in several big projects, okay, the energy is not gonna be so tiny like this. Okay, then it's appropriate to use the unit of joule. But once we are considering the tiny particle, for example neutron, we need to use the more appropriate unit, and we divide this amount, this quantity, by the electron charge 1.6 times 10 to negative 19. So we get more appropriate unit for that, right? So once you divide this one, say 3.277 times 10 to negative 21 divided by 1.6 times 10 to negative 19, so you're gonna get once you leave it into the calculator, right, you get 0.02, and it's in electron volt. Okay, and that's the units of the energy you could get due to the movement of the neutron. Okay, and that's called kinetic energy. All right. Yeah, we have already considered the tiny particle, right, like the neutron. Okay, so what about the big particle, like baseball? Okay, I guess that the author of this example would be in the United States of America, because baseball or American football are quite popular there, right? In the United States, right? But for us in Thailand, I'm not sure whether it's popular or not, right? Okay. Yeah. Let's talk about the baseball scale. Okay, this is the visible object by eyes, right? That's the object we could see by eyes. So let's say this is the ball, right? And it's called baseball. Right? Compare the bright wavelength for an electron. Oh, it's tiny. So let's say if this one is electron, right? And this one is the baseball, right? This is the baseball BB. Okay, baseball is much bigger than electron, right? And electron with this amount of mass moving at the speed 1 times 10 to negative 7 meter per second, and the baseball is moving at the speed not so high like that. Okay, not so fast like the electron. Okay, but anyway, it's 45 meter per second. Okay, 45 meter per second. And what about this quantity in the most noticeable unit? For example, in kilometer per hour. What is that? 45 meter per second. So if we want to convert these ones, so let's say this is Elico Fermi, right? Fermion. This is Peter Higgs, who discovered Higgs boson, right? And this is the Bose. The physicist used his surname to say to call another one type of the particle, which is boson, right? So and this Fermi, okay, let's say 45 45 meter per second to kilometer per hour. Oh my god, I'm still 45 meter per second to kilometer per hour. It's, you can see that the baseball speed is 162, right? And you may have watched the tournament of baseball competition or something like that, and the speed of the baseball is like in the high speed of the car, right? It's on at that level, 162 kilometer per hour. Any of you who would have ever sit into the car with this speed? Is there any of you who have ever experienced this speed in a car or in any train? Yeah, if you have ever gone or visited some countries like in Japan, in France, in Germany, in some other countries, you may have ever got into the high-speed train, or even in China, they would have the speed sometimes if they use the magnetic force, and there is no touching point between the railway and the train could go up to 400 kilometers per hour. That's very high speed. But for the general train that uses electricity, it's quite simple to reach this speed, right? 162. Okay, yeah, the baseball move with 45 meter per second, or in kilometer per hour, it's 162, right? Approximately. So you could see that the big object could not go. Oh no, it's not. It's positive, right? It's not so high as the tiny particle, which is electron, right? But anyway, mass of electron is 9.1 times 10 to negative 31 kilogram, right? And mass of baseball is much bigger, much heavier, right? It is 0.145 kilogram, right? Yeah. The question from this example is the comparison, right? They asked us to make the comparison between these two objects, right? The small one and the bigger one, right? So yeah, from the Bruyn's wavelength expression, lambda is given by h is given by h divided by mv, right? This expression h divided by m and v. So yeah, let's talk about electron first. All right. So lambda of electron will be h. Which is 6.626 times 10 to negative 34 and joule second, right? That's the unit for the Planck constant. And the next term is the mass, right? The mass of that object. And once we are talking about, once we are considering electron, we're gonna use 9.1 times 10 to negative 31 kilogram. Okay, and the next thing is the speed, right? The speed of the electron that is moving. So it's 10 to 7. 10 to 7 means 10 million. Okay, 10 million meter per second, which is very, very high. Okay, for the human movement. I think human movement could not reach that amount at all. Okay, and then you put it into the calculator. So to save time, I'm gonna use the result from the lecture notes, right? Because we waste our time during the setup. And yeah, the wavelength of electron is gonna be 7.27 times 10 to negative 11. Okay, negative 11 meter. So let's ask or let's consider whether it is possible or not to detect the wavelength on the scale. I would say it's not so far from the human ability, because human ability could detect the light, and the light is on the scale of 10 to negative 9, right? That's the light frequency wavelength, right? 10 to negative 11 is only 2 finer order from 10 to negative 9. So it's not so far from the human ability to detect the wavelength caused by electron moving at this speed. Okay, now let's consider the next thing, which is the baseball. A bigger object, right? Baseball. The lambda for BB baseball will be, of course, the same thing. The numerator is the Planck constant in the SI scale, 6.626 times 10 to negative 34, and Joule second in divided by the mass of the baseball, right? Mass of the baseball is over here. They just provide 0.145 kilogram. Okay, and the next thing is the speed. The speed is not so high. It's only 45 or 162 meter per hour, right? Yeah, and that's also 45 meter per second. So once everything is in the SI scale, we could immediately calculate it. Okay, put it into the calculator, and we're gonna get the lambda for the baseball as 10.016 times 10 to negative 34. Okay, and meter. Okay, and let's consider the reality. Negative 10 to negative 34 is a very, very tiny amount in at the moment. Okay, in 2021, at this year, no measurement device could detect the wavelength on this scale. Okay, you can use the formula and you can calculate it. You can see the theoretical value, but in physics we have to also consider the reality. And on this scale 10 to negative 34, there will be no measurement device that could detect the wavelength of the electromagnetic wave like this. Okay, it's not possible right now, but anyway, you could see the idea that the wavelength predicted by the Bruyn for the tiny particle that moves very, very fast, 10 to 7 meters per second, is in a considerable scale that human could detect. But for the bigger scale baseball, which is a kind of a particle, right? It's big. It could be observed by human eyes, but the wavelength that emerges is beyond the ability of human to detect. Is 10 to negative 34. Okay, so the comparison is the following: the wavelength of the baseball is much shorter than the wavelength caused by electron movement. Okay, and yeah, and the next question is compare this wavelength with that of an electron traveling at 0. You will see the full name of the full text of the example. Traveling at 0.999 z. Okay, you know z is the speed of the light, right? And what about the wavelength caused by electron? Once electron is moving almost at the same speed as the light. Okay, but before that, I would say no particle could be faster than the speed of the light. Okay, the speed of the light is the limit of the velocity or the speed of any object. Okay, but what about the wavelength caused by the movement of the electron at this speed? So once you talk about the particle that moves very, very close to the speed of the light, we are gonna need to deal with the relativity theorem, which is proposed by Albert Einstein. Okay, I hope that you have ever seen the theory of relativity by relativity theorem by Albert Einstein, right? ทฤษฎีสัมพันธภาพนะครับคุณเคยเห็นเนาะ and one of the quantity from the result by Albert Einstein is the relativistic momentum. Okay, relativistic momentum, and the formula, the general formula of the momentum is like this, right? It's P equal mv, right? And that's the classical expression for the momentum, right? But for the momentum of the object that has speed close to the light, you're gonna need the relativistic momentum expression, which is a little bit more complicated than the typical formula for I'm not sure what about the people in Zoom. Is there anyone who wants further to get into the Zoom classroom? No, huh? Okay, yeah. The momentum expression in relativistic theory is this one. Okay, it's yes, of course, it's the ratio relative. If V is okay, the denominator just emerges, right? If you move with the speed of light, you're gonna have c by c as number one, and this is 0, and your momentum is gonna be infinity, right? So that's valid for only the photon, but the photon has no mass. Okay, photon has mass of 0, so 0 times infinity is gonna remain 0 too. So momentum of photon is nothing, right? But for any particle, you're gonna need to substitute the mass of that object and the speed of that object too, right? In this one, and yes, you may calculate first the momentum, right? And if they ask you about the momentum, but it's not the case because they want to know the wavelength of the electron at that speed, right? The wavelength of the electron at the speed is going to be the Bruyn is going to be given by the Bruyn expression h divided by mv, right? Yeah, h by p, sorry, but p here is going to be this one from the relativistic theorem by Einstein. You substitute this one into this expression, you're gonna get here this one, right? This expression, and everything. The mass should be the mass of electron. The velocity should be the velocity of the electron, right here. Okay, and this is the cascaded ratio, and we move the denominator here to the upper part, which we're gonna have this one here at the numerator, and yes, we will substitute several quantities into that expression. Yes, here. Yeah, lambda of the electron, right? Lambda of the electron will be h by me and ve, right? And square root 1 minus V of electron divided by C and square, right? So let's substitute everything, which is 6, 2, 6, 10 to negative 34. And here the mass of electron, which is 9.1, 10 to negative 31. And the velocity, which is the 0.999. Okay. And the speed of the light, which is 3 times 10 to negative 8, and the square root 1 minus, and of course you know that VE, the velocity of the electron, is 0.99, right? Once you divide it by C, you're gonna have 0.999 square. Okay, and once you leave this whole numbers into the calculator, you're gonna get the wavelength caused by the electron at this speed as 1.086 times 10 to negative 13 and meter. And yeah, you can see that the wavelength of the electron at this speed, which is very close to the speed of light, is a little bit, is even smaller than the speed of electron at 10 to 5, right? 10 million meters per second, right? Yeah, it's even harder for us to detect the wavelength of the emitted photon caused by electron here. Okay, and หมดเวลาแล้วหรือยัง it's 1350, right? We're gonna reach our limit, right? Yes. In 1927, Davison Gamma at the Bell Lab, right? Bell telephone laboratory discovered the electron diffraction. Okay, not only wavelength caused by electron movement or electron speed. Okay, further behavior of tiny particle movement is independently observed by these two people, these two researchers, Davidson and Gamma at Bell Lab in the United States. Let's switch to the European continent. In Germany, Esterman and Stan demonstrated the alpha particle. Okay, alpha particle is the helium atom without electron at all. Okay, without any electron at all. That's called alpha particle. The alpha particle has also diffraction, and that's discovered by Esterman and Stan. Okay, you could see some detail of the discovery by two independent groups of researchers here in the United States and in Germany. More experiments revealed that the diffraction of low energy neutron and large molecules, okay, even the large molecule could have also diffraction behavior, and neutron with low energy could have also the diffraction behavior. All of this discovery gave a strong support to the Bruyn's hypothesis. Okay, the idea of the Bruyn is only the hypothesis. Okay, the idea on the paper, but no one have proved that. Okay, before 1927, no one confirmed the Bruyn idea is valid in reality. Okay, we have calculated so many things, the wavelength and so on, but in 1927 and so and onward, right? The people have made or discovered something that could verify the truth by the Bruyn, right? All of this discovery gave a strong support to the Bruyn's hypothesis, and yeah, and that's the whole story of the wave particle duality by the Bruyn's wavelength expression. Now we move to another tiny particle phenomenon, which is discovered by Werner Heisenberg. Okay, Werner Heisenberg is the physicist in Austria, right? In Austria, he found an inequality of the product of I'm not sure he's German or physics. Werner Heisenberg. Yes, he is German. I'm sorry for that. Yeah, Werner Heisenberg is a German physicist, and he proposed the idea, right? Because when you are dealing with the particle, which is very extremely small, it's really hard for us to detect, right? And in reality, the physicists like Heisenberg has discovered that there is no exact point for the tiny particle at all. Not only electron. Okay, for any particle that is extremely small, what we could say is only the prediction, and the prediction should have mean value and the difference of the possible location of that object, and that's called uncertain coordinate x, okay, of any object. Let's say if you stay here at the point, the reference point, and you see the particle like electron, and you could not measure the exact location of electron at all, but what you could see is only the delta x location. Okay, electron should be in this range, okay, and the momentum, because the tiny particle would also move, right? So the momentum could not also be predicted simply by that one, okay. And what the physics could predict is only the corresponding uncertain momentum, and that's called delta px, right? Delta px is the uncertain momentum of the tiny particle. Whatever particle you are watching, whether it's neutron, proton, electron, or electron, neutrino, whatever that has mass, okay, it should follow this expression. What about this expression? The expression by Werner Heisenberg is delta x, delta px, okay, the uncertainty along the x-axis is greater than h by 4p and 1 by 2, or you know that h slash is h by 2 pi, right? In terms of h slash, which is the reduced Planck constant, it's going to remain half the reduced Planck constant 1 by 2 of h slash, right? That's the Werner Heisenberg expression. Okay, it's unfortunately we could not find the exact location of the tiny particle. Okay, it means that in general, neither the momentum nor the position of any particle could be measured simultaneously and with arbitrary great precision. Okay, as classical physics would predict. Okay, for a big object like a car or your body, you could measure precisely, but it's not the case for the tiny particle. Okay, because this chapter is talking about something in the atomic scale, right? So it's tiny. So in order to completely understand the formula by Werner Heisenberg, we're gonna use the equation 65, right? For one example, an electron is confined inside a cubical box. What is that? It's a cubic box, a cubical box. Somehow it is, right? Okay, that's the cubical box. Yes, and one side of the cubical box is 1 meter, like this, okay? And of course, in other side, it's gonna be 1 meter too. in yeah, this side too, right? 1 meter. And yes, estimate you multiply m and divided by m of to this expression, you're gonna get m squared v squared by m, right? And yeah, once we know p is equal to mv, it's gonna be 1 by 2 p squared by m, right? So we're gonna apply this expression to the electron, right? Kinetic of energy will be 1 by 2 mass of electron. Oh, you know, it's momentum of the electron divided by the mass of the electron, right? So it's gonna be 1 by 2 in 5.273 times 10 to negative 25 square and divided by mass of electron, which is 9.1 times 10 to negative 31. All right. And once you leave these numbers into the calculator, you're gonna get the minimum of the kinetic energy, which is 0.952 electron volt. Okay, you convert the energy from the Joule scale to electron volt by dividing it with 1.6 times 10 to negative 19. Okay, you're gonna get the result in electron volt unit like this. Okay, and anyone who would like to join in soon? No, nah? Only Shayasit, right? Shayasit. This one, right? Yes. Let's get back to our story. We now reach the next example about the Werner Heisenberg uncertainty, right? The speed of an electron is measured to be okay, we consider the same particle, electron, right? 5 to 10 to 3, which is 5,000 meter per second. You could convert to kilometer per hour yourself from any calculator, and to an accuracy of 0.003%. So very tiny. And find the minimum uncertainty in determining the position of the electron. Okay. So what is min? Minimum delta x. What is that? Okay, minimum delta x min. Yeah. You could start from the general expression, general information given in this example. They say the speed of electron is measured to be, okay, the mass of electron. So delta V, right? Delta V of electron. Delta V of electron is found to be 0.003 by 100 times the speed, right? The actual speed is the actual speed of the electron is, this is the mean value, right? Which is 5 times 10 to 3 meter per second, right? And yes, that's VE, right? And you know from the Werner-Heisenberg, right? Werner-Heisenberg expression says delta x and delta px is greater than, it's not equality, right? It's greater than h by 4 pi, right? And if you want to find a minimum of delta x, minimum of delta x will be equal to you move px to the right hand side, you're gonna get h by 4 pi, right? And delta px, okay, delta px, and that's the uncertainty of the uncertainty of the momentum of any object along the x-axis, right? And let's consider delta px, which is m and v, right? But it's the uncertainty of the velocity of the electron. So this is the mass of the electron, right? So we're gonna substitute this one into that expression. So we get a minimum of delta x as h by 4 pi and mass of electron and delta VE, right? So we will substitute everything into that expression. 6.626 times 10 to negative 34 and 4 pi times the mass of electron, which is 9.1 times 10 to negative 31, and the uncertainty of the electron speed is this one, right? So you, oh no, why, what happened? You can cancel this one, right? Cancel this, and you get 0.003 times 50 only, right? It's 50. All right, it's I don't know, 10 0.15, okay, meter per second, okay, and that's the uncertainty of the electron speed, right? 0.15 meter per second. And yeah, that's the whole thing. Once you leave these numbers into the calculator, you're gonna get the result, right? Which is it's approximately 0.385 and 9, okay, in millimeter, okay, and that's it for this example. So the time is over now. So let's finish our problem right here, and we're gonna have we need to have the, I don't know, the homework, right? The homework is something about Werner Heisenberg along the x location, or the, I don't know, yeah, Werner Heisenberg or the energy wavelength or the radius of the bigger atom, which is called hydrogen-like atom. Okay, I will create the homework template in the Google Classroom later. Okay, if you have any questions, so let's finish our lecture of today. So if you have any questions, just let me know, and if not, we're gonna see each other. Okay, Friday is the last day of the year, right? It's New Year's Eve, so we would not have the lecture, and see you next year. Okay, bye bye สวัสดีครับ พบกันปีหน้าครับ การบ้านเดี๋ยวสั่งใน Google Classroom ให้นะครับ บ๊ายบายครับ สวัสดีครับ It's not entertaining. is entertainment. Yeah.